Okay, so today we will start with a new concept. Okay, it's still about classification, and this time we do decision tree. This is quite different from what we previously discussed, because previously what we discussed most, I believe all of them, is that we used the gradient descent. And to update the weights. And we based on, so for the update of weights, we use the cost function. Some SVM, we call it loss function, the cost function. And do the derivative, that's the gradient descent. Okay, so that's a general idea regarding all previously what we learned. Today we will learn it involves some kind of tree, and we call it decision tree. Okay, and this is also for classification. And then let's see the concept. Okay, so in decision tree learning sets, there are two. Okay, updated one is C4.5, and the previous is ID3. It's iterative dichotomous 3. Okay, so this is an algorithm. Here it's who invented Ross-Quillen. Okay, so generate a decision tree from the data set. So we have the data, if you recall, then it's going to generate some tree. Okay, and it's typically as used in machine learning and natural language processing domain. Okay. And then C4.5 is an extension, okay, to the earlier version of ID3. So if you see ID3 or C4.5, and then you know they are referring to a decision tree. So that's just some term. Okay, then next let's see what is a decision tree classifier. Okay, and just also keep the mind is decision tree is very good at interpretability. Okay, it's not like what we have learned so far of those use gradient descent update the weights. Basically, we have no clue what's inside. Is it how the weights is updated? Which feature is important and which feature is not as important? Some of those, is it? It's kind of a black box. But for decision tree, it's a different story. So here it gives a diagram about the general idea about decision tree. So decision tree basically it's you're going to break down the data, okay, the data set basically by making decision based on a series of questions. Okay, so that's the idea about decision tree. So here it gives some idea. Okay, gives a tree example. So you have some, so over here it's a full data set, is it? And you want to do some classification, okay. Then in this case, the first question is we'll go ask, work to do. Do you want to do some work? Is it? Okay, if your answer is yes. So some people may say, okay, yes, I'm going to need to do some work. Then you need to stay inside. Is it? Otherwise, some say, okay, I prefer not to do my work. Okay, then you want to maybe go outside. Is it? Then you need to check if the weather is good. Is it? Okay, if the weather is good, then so sunny day, is it? Then you say, okay, we can go to beach. Is it? If it's overcast, is it go running? And if it's raining, then you got to stay inside. Is it? Then you may say, okay, you want to check if a friend's busy. If a friend's busy, then you stay inside. Otherwise, you go to say movies. So for each branch, is it? So the sample size getting smaller, the sample size getting smaller, is it? And all these are the leaf node. And for the leaf node, basically it's classified, is it? And the internal, so in the middle, so over here it's the questions, series of questions. Basically, it's also filtering conditions, something like that, is it? So this is the basic idea about decision tree, okay? And before we move on to the next page, probably let's first see another one, the decision tree. Where is my, hold on, okay. No, not this one. I need to sharing and show all window. I need to find, yeah, this one. This is generated by our, okay. So can everybody see this? So basically this is, if you recall previously, we do that iris flower classification. If you recall that three kinds of flowers, there's a setosa, versicolor, and the virginica, etc. And based on, there are 4 features. But over here, we just use the petal width and the petal length, just use this 2 feature, okay, using this 2 feature. And here is the decision tree result. So you can clearly see this is different from what we previously discussed. Is it? In this example, this is the first question, basically, based on petal width, if it is less than 0.75. Is it? And this is total samples, is it? And each class, basically you have 35, something like that, is it? And then based on this, is it? So the first condition you check is based on the width of this. Okay, if it is true, then you reach the leaf node. And the leaf node, basically, all the samples, is it classified for this range? Then the left will be another 70 samples. And that samples, all those samples belongs to false, is it? So greater than 0.75. Then you may check, okay, if it's less equal than 4.75, is it? And based on the classification for versicolor, is it? Then we have 2 branch again, is it? So for this one, this is a leaf node. And this time you have 30 samples for within this range, is it? So you got those 30 out of the 70 samples. Then for the remaining 40 samples, then you need to do what? You need to do the classification again. Is it? This time you change the question again. It's 5.15. Is it? So, and we can continue. Is it? So in this example, then it's continue. You can see the tree is quite deep, is it? And for all of the leaf nodes, is it? For all of the leaf nodes, then it is what? It is the sample classified as a specific flower. Okay. So this is regarding the decision tree general idea, okay? And then next, let's see. So we kind of get the picture of decision tree and how decision tree make the decisions for each branch. So here it explain more about decision tree classifier. So decision tree classifier is white box type of machine learning. Okay, because if you recall, for each branch, is it we can see the condition, is it? So it says it we got to know the internal decision-making logic. This is completely different from the gradient descent. The gradient descent, we have no clue, is it internal, how the samples go to which class? We have no clue, is it? Because it's just based on the gradient descent and then got back, and it involves the iteration, the update the weights, is it? So for the other type, like neural network, or like previously what we already learned, so they are considered, later on we will learn neural network, okay? The black box, so we don't know what happened. Is it step by step, how you come up with the weights, the optimal weight. So, but the decision tree then gave us a clear idea of internal decision-making logic, is it? And because of this, okay, then the training time, it's said it's faster. Because it's based on condition, then you filter out certain samples, okay, compare with like the neural network, the black box one, okay. And as to its time complexity, is that it's a function of the number of the records and the number of attributes, the features. Okay, and the decision tree is also a distribution free. So it doesn't, we don't need to worry about the parameter tuning. But of course, later on, we will also see not just decision tree, some other like the ensemble ones. Then we also need to take a look at some of the parameter. But over here, we don't need to worry about like the regularization. So is it like the regularization, the C and the gamma, like for the SVM, is it? Then for those, we don't need to worry, is it? In this decision tree. And decision tree says it does not depend upon the probability distribution assumption, okay? And decision tree, it can also handle high dimensional data with good accuracy, okay? So this is regarding the general benefits for decision tree, okay? And then what next? Let's see. It's so decision tree, basically it's transparency, is it, based on previously we discussed, and also the computation cost is low, okay. Decision tree, later on in our example, we will also see it's also quite helpful in exploring data, okay, before we apply other algorithms. So sometimes you can use decision tree to pick up, to filter out, basically, important features. If you have a lot of features, is it? So sometimes you can use decision tree to help you pick up some important features that's going to make a critical impact for the classification, okay? ISS is also helpful for check the quality of engineered features and then identify the most relevant ones, okay, by visualizing the resulting tree, okay. So we can previously the iris flower one, etc. That tree, is it? It's generated later on. We will see in our program. You can generate that tree. That it also quite helpful for visualization, okay, of the tree. As it's the downsides, so the disadvantage of decision tree is what? It's they tend to overfit. Okay, overfit, then it's lack the ability to grasp the relationships between features. Okay, so that's the downside. And later on, we will see the random forest. So we ensemble, we put multiple decision tree together that can then help relieve this kind of issues. Okay, so this is just regarding decision tree discussion, upside and downside. And then next, let's see, when we do the decision tree, we start at the tree root, that is some condition, that, and then you're going to split the data. So for tree data structures always like that. You're going to split. Is it split based on what? Feature. Is it? And the feature will result in what? Largest information gain. Okay, so it's based on this largest information gain. Okay, later on we will see this. So this represents information gain. So what is that? We will see. Okay, and then in an iterative process, is that we are going to repeat this splitting procedure at each child node until the leaf nodes is reached. Okay, so this is how you are going to do the split. Okay, and in our example that RS1, we can kind of already see the tree sometimes can be very deep. Is it very deep? Then it can lead to overfitting. Okay, overfitting. And it says to prevent overfitting, sometimes we can limit the maximum length of the tree. So in our example, we can also see you can set up. Okay, it's also kind of like, if you recall, for gradient descent, is it we set the number of iterations for the convergency. Because sometimes if you just use the nature convergency, the offset some small number, then it may take quite a long time to converge, is it? So then we just define certain number of iteration, let it iterate like maybe 3,000 times or something like, or not 300 times, is it something like that? Okay, so that's regarding decision tree, more discussion. Okay, then what is the next we are going to discuss is how do we, so information gain, is it? And we try to maximize when we do the split, is to try to maximize the information gain. Okay, so this is going to be the objective function for the decision tree. So at each split, okay, so over here, it also gives us the description about the terms. Okay, so what is this F? It's regarding some feature. That, if you recall previously, is pedal length. Pedal length. Is it? So that's the feature. Is it for the split? Is it for the split? And what is DP and DJ? Is it? That's the data set of parent and the child node. Is it? So you have this. So, and then here you have. So this then going to consider as parent node. Is it? And over here, this is child node. Okay, so parent node, child node. And what is I here? I is impurity measure. Okay, and how do we measure later on? We will see. Okay, there are different approaches for impurity measure. And what is N? N is the number of the samples at the node. Okay, if it is P, then it's parent node. If it is J, then it's the J's child node. Okay, so that's regarding the information gain. And the information gain basically is describe what? The difference between the impurity of parent node, and here is the sum of of the child node impurities. Is it? So child node, if this is lower, then the information gain is higher. Is it? The larger the information gain. Okay. So information gain basically just keep that in. It's the difference between parent-child and all of the parent node and all of the children's nodes impurity. Okay. So this is regarding and the information gain. And generally speaking, for like sklearn, normally to reduce the combinational search space, okay, we do the binary decision tree, if you recall that diagram shows. And of course, you can have multiple ways that for the branch, is it? But over here, we just pick 2 branch. Is it? So this is regarding binary decision tree. Therefore, binary decision tree, then you just need to consider the left child and the right child. Is it? To minus them from the parent child. Is it? Okay, so that's regarding information gain. Okay, then let's see this term. Is it? That's regarding impurity measure. Okay, for impurity measure here, we are going to discuss 3 impurity measure. Okay, 3 impurity measure. And it's the 3 one, it's Gini impurity, so IG. Entropy is called IH, okay? And the classification error is IE, okay? For our binary decision tree, okay? So those regarding the impurity. And let's take a look. How do we use an example? Okay. Oh, let's still go back here. Example to take a look about the impurity. So how to calculate the information gain, okay? And the objective function, remember, is to try to maximize at each split, okay? So that's the overall formula, okay, for our information gain. And then for the binary one, we already saw this. Is it? Just left and right? Is it? Okay, so here it gives a very, very simple, just let us get some idea, okay, about the calculation of this impurity, okay, in different scenarios. So in this example, total, we only have 80 samples. Okay, 80 samples, and we have two classes for the data. So each one of it is 40, okay? And so over here, there's some decision, assuming like a pedal length, is it less than the 0.75? Is it? So anyway, we can just assume, okay, this is pedal length less than 0.75, is it? And then you want to see if it's setosa, is it? So that kind of flower, is it? Okay, so anyway, based on this check, then you find, okay, maybe this is yes and this is no, is it? Okay, then for this one, what you get, this is a child node. You have 30 and 10, and for this you have 10 and 30. Okay, so that's scenario one, scenario A. Okay, this is considering scenario B. Is it scenario B? Maybe you use some different criteria. Okay, so you still have 40, so total 80 sample, but maybe this time it's pedal width. is it? And maybe less than 0.5 something, assuming, is it? Then you go to same thing, is it? You get two branches, okay, one with this and the other one with this, is it? Okay, we have the specific data here. Then let's see. So the first one is the impurity is regarding the arrow for the impurity calculation, is it? So the formula to calculate is it's 1 minus maximum the probability belong to certain class. And here this T represents a certain node, okay, maybe parent node, maybe child node, okay. Then let's see. Okay, so for the parent node, so this is a parent node, it's entropy, or not entropy, it's impurity for the arrow one cases, is it? Because it's the, you pick the maximum probability, is it, among all of the probability, okay, belong to a certain class at that node. And over here, we first discuss the parent node. For parent node, for both A and B, there is no difference. It's 40-40-ish, is it? So that's why the probability is it, over here, it's 1 minus this maximum, but you only have one case, is it? So that's why it's 1 minus 0.5. So you get to 0.5, okay? So that's this case. And then for the second level, is it? We come to this. This is the left child impurity, is it? So what is impurity is maximum probability, then you have 3/4. You have 1/4. Is it the probability, okay, between two, this class or the other class? Is it, that's a probability. The maximum one is 3/4. Is it? So that's why you do 1 minus the maximum one. Then we get the impurity at this left child node. And for the right child node, is it, we get what? Same thing. This is 1/4. This is 3/4. Is it? And then you minus, so you get the impurity. Okay, impurity. And then the information gain, is it? Information gain, then it's the parent one minus, so these are the impurity from the child node. And what over here is based on what? Child node, not over, so the specific node here, is it? So here you have 40/80. So that's how we come up with 4/8, is it? So same thing here, is it? So total you have 40, then you have 80, so you have 4/8. Is it? Then times is the impurity. So that's how we come up with this number, okay? So then we got, this is a parent one, and then we got to the information gain is this number. So 0.25. And then same idea for the writers, for case B, is it? For this case, then you can calculate its left child's impurity and the right child's impurity, is it? Right, because it's all samples, is it, belong to one class, is it? So that's why its probability is 1, is it? Is 1. So that's why its impurity then is 0, okay, impurity, okay. And because it's just a single class, it's pure, is it? Here you measure impurity, is it? So that's why it's 0. And then it's information gain, it's this case. And then for the split, then we can see based on both of this case, these two cases, no difference, is it? The information gain for these two, okay. Okay, so this is regarding the impurity calculation with error. Okay, so what next one? Let's see. The next one is to discuss. It's called Gini impurity. Okay, Gini impurity. For Gini impurity, it's a calculation. Then it's belong to certain probability, a certain class. So C over here, it's a class. So it's a summation over all class, over all classes. Is it over all classes? So the probability at that node, is it to the class? And this one is not that class, is it? So that's how we come up with this expression. Okay, so then similar idea, is it for the parent one? Is it for parent one, if you recall, it's 40, 40, is it? So that's how it comes up with, because there are two classes, is it 40, 40? So that's how you come up with 0.5, is it? So your summation, both of the belong to class 1 probability and belongs to class 2 probability, is it? Then you square, and then we come up with this value. Okay, and then for the left child, in case 1, for case A, is it? Then it's a probability, is it? Probability for class 1 and the probability for class 2, is it? And we sum that. That's how we come up with this value. Okay, and then for the right branch, you also get this value. And then for information gain, we can say this time it's 0.125. So it's compared with the previous one, it's 0.25, is it? This is not as good as the previous one for Gini impurity. And then for case B, it's the same, say similar calculation, is it? And here we have the information gain for the case B, as compared with the previous one, it's 0.25. So it's not as good as the previous one. And for the third impurity calculation, is called entropy, is it? And entropy is said for all non-empty classes. So the probability is not 0, is it? Then the calculation for its impurity, it's based on this expression. Okay, so the probability at the node belong to certain class is times you take a log of it. Okay, so that's the probability. Okay, and if all sample belongs to the same class, then its entropy is going to be 0. Okay, and if uniform distribution, then it's the maximum value. Okay, so that's what this tells us. Then similar, we can conduct the calculation for the parent one, is it? And we can get its impurity as 1. And then for the case A, it's left, we just follow the same one as for each class. Is it? So this is class 1, class 2 cases, is it? Then we get the impurity, and then we apply the number of the child node for the overall, as it times its impurity. Then we get information gain for this case. And for case B, then this time we can see its information gain is better. It's 0.31. It's better than 0.25. Okay. So over here, it's just give us a pretty simple example to explain the concept behind the impurity calculation, okay, for all 3 different cases. And then let's get back here, is it? So our goal is to maximize the information gain, okay? And all of this we already explained using our example. So the Gini, impurity, etc. And over here it says in practice, it says both Gini and entropy normally yield similar results. Okay, so it says not worth spending much time on evaluating tree using different impurity criteria. Okay, but we do need to experiment with what? Different pruning cutoffs. So the depth of tree. Okay, this you need to experiment to find the optimal one. You don't want it to go too deep, because too deep may lead to overfitting. So may not generalize well. Okay. And this is for the classification error one, etc. And it says for this classification error ones, normally it's at a useful criteria for pruning, okay, but not recommended for growing tree, okay, because it's as less sensitive to the changes in the class probability, okay. So the three different impurity calculation for the classification error case, then it's good for us to do the pruning, okay, to make a decision about how deep the tree should be. That helps. And for the other two, normally there is no huge difference, okay, Gini, impure, or entropy. And over here, to more discussions that the deeper the tree is, then the more complex the decision boundary will be. Then previously we also see that can result in overfitting. That if you recall, previously for SVM, zeta gamma 1, etc. So then it's very bumpy and very kind of enclosing, etc. So that can lead to overfitting. So we are not generalized well. Okay, so for the decision. And also for decision tree, normally we don't need to worry about feature scaling. Okay, so it's not a requirement because over here it doesn't involve like the gradient descent, that calculation. So we don't need to worry about feature scaling. Okay. And the sklearn also allows us to export the decision tree as a data file here, it says. Okay. And then it said it can be visualized with the graph, with program. And so decision tree may lead to overfitting, etc. So the next concept regarding decision tree is random forest. So what is random forest? It's ensemble of decision tree. So multiple trees together, multiple trees, etc. So the idea that behind it is what we are going to do. You have more than one decision tree, is it? Then you're going to average them so that you can kind of balance off the individual's high variance. Okay, so that we can build a more robust model that can give a better generalization. Okay, so that's regarding random forest. So random forest use multiple trees. So random forest general idea is said like this. And the first step you're going to do is you're going to draw some random samples of size. So randomly choose the samples from the training set, but with replacement. Okay. Then we can do a decision tree, grow the decision tree, etc. And at each node, what we do, we randomly also select a feature. So we are not going to use all of the features. We random select some feature. Then you split the node using the feature that provides the best result. Okay, then we can repeat these steps for certain number of times. Then we aggregate all the predictions and assign the class label by the majority vote. Okay, so suppose if you have like 10 trees, is it maybe 7 trees predict as class 1 and 3 trees as class 2? Then you just with the majority vote. Okay, that's what the majority vote means. Okay, that's the random forest. Okay, but it says random forest don't give same level of interpretability as decision tree. Is it? Because decision tree, clearly we have that tree. It's very transparent. But random, because you combine multiple together, you average it. Is it? So definitely it's not as interpretable as the single tree. Okay. But the advantage is we still don't need to worry about like good hyperparameter values. Is it? And it also says no need to prove random forest tree. Okay, random forest, because it's ensemble model, it's already quite robust to noise. Okay, and the number of tree, okay, then it's important. And of course, the larger number, the better performance. But of course, it costs more. It costs the computation more. And also over here, we said the feature selection. That if you recall previously, okay, the number of features. So the number of features, generally we are not going to use all of the features, okay. So we are going to pick some of the features. And then how about what is the best number? Is it? So here it also gives some recommendation. So the number of features for a random forest. So M is the total number of feature. Okay. So you take a square root of it. Then that's a good choice, okay, for the number of features at each split, okay. So this is the general idea, background, theoretical information regarding the decision tree. What next? Let's take a look at the example, okay, to have better understanding. And then from this example, you can see it's also quite straightforward, okay. And continue with that chapter 03 sklearn one, okay, on the iris flower, okay. In that example, it also gave us the Gini entropy and the classification arrow for the impurity calculation, and it just used some certain range of data, okay, and gave us the diagram about the impurity result, okay. And what next is in sklearn, okay. If you want to use a decision tree, so this is regarding single tree, okay, then you need to import the model, and same as usual, is that you need to create an object of the tree, is it? And here you can specify the impurity. Just remember we have 3, is a Gini entropy or classification error, and you can specify this maximum depth. This is the pruning of the tree depth. So here it looks like it's only allow 4, okay, 4 level. And then after you have the model, then you can fit the model, okay. And we can also collect its accuracy. So this is as all with what we previously learned, is it? And you can see the accuracy is also quite high. This is the decision boundary plotting, okay. So it's pretty good. And if you recall previously, we also said decision tree is also quite helpful for feature importance. Okay, feature importance. So you can collect the feature importance in sklearn, and then you need to, is that because it's the decision tree regressor, okay, and the decision tree classifier, okay. So the model provides feature importance property, okay. So we can directly, so you have that tree model, is it? Then you can just directly get its feature importance, okay. And over here, we enumerate the feature important. And here we just have two features, okay. Consider petal width and the length. The length, okay, we just consider. And we can then find its importance, okay, feature important. And here is the feature importance, is it? And we also show it plotting in bar plotting, is it? So it's we can clearly see this feature, second feature, importance is higher than the first one, is it? So this is regarding kind of also, because if you have some case, bar case like this, then that means this feature is not important that much, is it? If you don't need it, you can get it out, is it? So decision tree, because this case is just quite simple, just have two features. And if you have quite a number of features, then maybe sometime when you do the model training, maybe you just want to pick the top 10 features, something, is it? With those feature that doesn't contribute more, maybe we can ignore that. So, okay, so that's regarding feature important. And then what next show is use different impurity. Here we use entropy. So we can see the result is pretty close, okay. And the feature importance, this time it's the feature importance offset is larger than the second one. We can still see the second one contributes more, okay. And over here it's regarding how do we do visualization, okay. Do the visualization, then if we want to generate that image, then you need to, from this package pi.plus called, okay, import this graph from that data, etc. And then from the tree, we import that export graph visualization, is it? And then you can provide that tree model, etc. Then you specify class name, feature name, etc. And then over here, you can call that write. In this case, is a PNG file. Okay, so that's the file. If you recall previously, we show our decision tree for the RS1, etc. So that picture basically generated by our by this export graph visualization. Okay, so your decision tree, you can save it, is it? And what is the next one trying to show is a random forest. Okay, random forest from ensemble. Okay, so it's not a single tree. Okay, and you can still specify the impurity criteria because it involves number of more than one trees, is it? So the estimator, this one, basically it's regarding number of trees. Okay, number of trees. And this number of jobs, this is if your computer has multi-core, okay, then it can support parallel processing to expedite your algorithm, okay. And over here it also gave us the boundary plotting, etc. And for this forum, you can also collect feature importance. Okay, so it also allows, and then in this case, it's different. We can see the result is different from a single decision tree. Okay. Okay, so basically, so today we finish decision tree and random forest. Okay. So that's all for today. Any other question before we dismiss the class?